Good afternoon. I'm SnehaP and my project topic is optimization of the Viola-Jones face detection algorithm. Now let's see what face detection is. It is a technology that determines the locations and sizes of human faces in arbitrary images. It detects the facial features and ignores everything else in the background. Now, this has major applications in the field of security, commercial applications, law and order enforcement, and the most recent being energy conservation. And even in the social network services, it has become a buzzword. It is really one of the fastest and widely emerging technologies ever since 2001. It is followed by face recognition, which has seen significant growth and has eclectic applications. Like you can see, be it the areas of entertainment, smart cards, information security, or law enforcement. Uh, because what our face is, it's one of the identity. It's a unique identity that we have. So it can be used in as our unique identity for smart cards, that is driver's licenses, immigration, national IDs, passports. Then it can be used for surveillance, that is security. And now in the latest and the most happening technologies is that of the augmented reality, which is used in gaming. Even face recognition is used in that. So what we are doing in this project is we are using Viola and Jones technique. Why are we using this technique of all? Because it's one of the fastest and the most robust method, and it is 15 times quicker than any technique, and it has accuracy rate of 95% at around 17 frames per second. Let's see what the process is like. What happens is, first the input image is fed and how the algorithm works. The Firstly, for any face detection algorithm, the gray level conversion takes place. Then it is processed. The sum window processing takes place, and the potential object regions are detected, and then they are finally localized to get the final output image. Let's talk about the approaches that are being used. There's the first one being the knowledge based method. In this, encoding what constitutes a typical face, example the relationship between facial features, is taken into account. Then we can talk about feature invariant approaches. Here, the aim is to find structure features of a face that exist even when pose, viewpoint, or lighting conditions vary. Then there is template matching, where several standard patterns stored to describe the face as a whole or the facial features are separately. Now, the technique which we are using here is an appearance based method. Here, the models are learned from a set of training images that capture the representative variability of faces. It is also important to know the pros and cons of each approach, so let's talk about that. Many algorithms implement the face detection task as a binary pattern classification task. That is, the content of a given part of an image is transformed into features, after which a classifier trained on example faces decides whether that particular region of the image is a face or not. Often, a window slicing technique is employed. That is, the classifier is used to classify the portions of an image at all locations and scales as either faces or non-faces. And then finally, images with a plain or static background are easy to process. Remove the background and only the faces will be left, assuming the image only contains a frontal face. Here we are in this project we are seeing about a single frontal face. We are detecting single frontal face with accuracy. Also, there is this method wherein we use skin color to find face segments, but it is vulnerable in nature. Why? The database may not contain all the skin colors possible. Even lighting can affect the results. Non-animate objects with the same color as skin can be picked up since the technique uses color segmentation. The advantages are the lack of restriction to orientation or size, but still it is not accurate. Now the other compare on comparing it with other algorithms. Template based matching assumes a set of templates to be fed into the algorithm, and this limits the objects that are detected by the algorithm. Then, on an HSV based model, it requires the color parameter of the object to be uniform and accuracy drops down considerably, whereas in our technique, we use a set of weak classifiers to obtain a final strong classifier that improves the detection accuracy, and the fact that there is a training stage before the detection stage allows the algorithm to be a general purpose object detection. Now let's talk about the goal. Goal for any face detection scheme is to identify and locate human faces in an image, regardless of their position, scale, in plane rotation, orientation, pose, or illumination. The first step for any automatic face recognition is to detect upright frontal image, a face with certain ability to detect face with different pose, scale, and illumination. We are using the frontal face recognition. Now let's talk about what this whole technique is about, how it works, the workings, and how did it come up. It's in this technique. It is there are three major contribution, or that they're like phases of the algorithm. First is feature extraction. What happens in feature extraction? The rectangular features are used with the new image representation, and their calculation is very fast. The next is classification using boosting. In this, the classifier training and feature selection using a slight variation of a method called adapt boost is taken into account. Then the third one being multi-scale detection algorithm, which is a combination of simple classifier and it is very effective. Okay, so the fundamental concept behind this technique is use of Hall-like features. They are the components that actually make up this process. Let's see what are they. A Hall-like feature considers adjacent rectangular regions at a specific location in a detection window, sums up the pixel intensities in each region and calculates the difference between these sums. Like for example, we have an image database with human faces. It is common observation that among all faces, the region of the eyes is darker than the region of the cheeks. Therefore, a common Haar feature for face detection is a set of two adjacent rectangles that lie above the eye and the cheek region. Now, this difference is then used to categorize subsections of an image. The position of these rectangles is defined relative to a detection window that acts like a bounding box to the target object, the face in this case. As you can see in this figure, the differences can be between two different features, or like say cheekbones, eyes, or nose. They're represented by these features, these components. And you can see the difference, so we can use these components to actually describe the whole feature, a facial image. Okay. In the detection phase of the framework, a window of the target size is moved over the input image, and for each subsection of the image, the Haar-like feature is calculated. The difference is then compared to a learned threshold that separates non-objects from objects. Because such a Haar-like feature is only a weak learner or classifier, a large number of these features are necessary to describe an object with sufficient accuracy. In our method, the Haar-like features are therefore organized in something called a classifier cascade to form a strong learner or classifier. Like you can see in this image of Lena that the differences between eyes and cheekbones, it's represented by one Haar-like feature here, and so on and so forth. There are differences being represented by a different Haar feature, and in the end finally everything is combined to give the exact deterministic phase. The extraction of features. Features are extracted from sub-windows of a sample image. The base size is 24 cross 24 pixels. They're scaled and shifted across all possible combinations. And in this, there are about 160,000 possible features that are to be calculated. And the features are basically 4 types, like as you can see in the image. Yeah. And they're very easy to calculate. The white areas are subtracted from the black ones. A special representation of image sample called the integral image makes feature extraction faster. Let's see what this integral image is all about. It can be defined as two-dimensional lookup tables in the form of a matrix with same size of the original image. Each element of the integral image contains the sum of all pixels located on the up left region of the original image, and this allows us to compute the sum of rectangular areas in the image at any position or scale using only 4 lookups. Like as you can see in the figure, we have A, B, C, D, and how we are calculating the sum. C plus A minus B minus G. They belong to the integral image I. The same thing. Now let's talk about the second phase. Now the next problem that is to be tackled is we have to select a subset of relevant features which are informative. That is, we need to model a phase. So a very small subset of features can be combined to form an effective classifier. Now how is it done? It is done by using AdaBoost algorithm, which stands for adaptive boost. It constructs a strong classifier as a linear combination of weighted simple weak classifiers. In this, every feature is capable of acting as a potential weak classifier. This algorithm determines the optimum arrangement for the feature polarity and threshold. For this, it makes the use of a simple brute force technique. Like you can see, a strong classifier is constructed of weak classifiers, which are actually each representing a single feature. Which one to choose? We have to choose the most efficient, the one that best separates the examples, the lowest error. Choice of a classifier corresponds to choice of a feature. In the end, it chooses a T feature strong classifier. So it is used to select both a small set of features and train strong classifier. This is how it works. It starts with uniform distribution of weights, and then it selects the classifier with lowest weight, and it keeps on increasing the weights on the training examples. Then at the end, carefully, linear combination of the weak classifier obtained at all iterations, and it forms a strong classifier. And the third and the final stage is the cascading classifier. In this, what are the goals? It's feature computation, selection, and real timeliness. Feature computation meaning features must be computed as quickly as possible. It should select the most discriminating features and must focus on potential positive image areas. As you can see in the figure, let's talk about how it works. On average, only 0.01% of all sub-windows are positive. Equal computation time is spent on all sub-windows. Must spend most time only on potential positive sub-windows. A simple two-feature classifier can achieve almost 100% detection rate, 50% FP rate. That classifier can act as the first layer of a series to filter out most negative windows. Second layer with 10 features can tackle harder negative windows which survive the first layer, and so on. A cascade of gradually more complex classifier achieves even better detection rates. Like the core behind the whole cascade classifier is what basically is done in this. All the non-images are rejected first, because it is easier to reject a non-image than to select an image out of the whole background. So as soon as it detects a non-image, it keeps on trashing it, and it just selects in the end. It just selects the image that comes after rejecting so many non-images. So this is like reject sub window, and it keeps on further processing, and this is how it is cascaded. The principle of this algorithm is to scan the detector time and again through the same image, each time changing to a completely different size. And sometimes there are situations wherein an image should have more than one face. In such a case, the evaluated subwindows result in being negatives. So instead of finding faces, the algorithm discards non-faces, like I discussed earlier. And this type of classifier is composed of stages. Each stage here further consists of a strong classifier. Each stage helps in determining whether the subwindow is a facial region or not. If a subwindow is classified as a non-face region, it is immediately discarded. On the other hand, a subwindow is in the case where it is classified as the maybe face is passed on to the next stage on the cascade. When a subwindow passes several stages, it is considered most likely to contain a face. So this is how the algorithm works. Rejecting the non-faces and selecting, maybe faces. And in the end, we get, with a 95% accuracy, we get the detection. So this was the output without the optimization. That is, in the Viola Jones code, the basic code, there were many detection windows that were obtained. But what I did was I calculated the mean of these windows, and towards the end of it, uh, optimized to give a code, which was optimized the code to give an image which is just one single window, like in this. And as you can see, it is properly detecting the face with just one window. Let's have a look at a running code. I'll take my own picture, and it is a frontal view. Let's see whether it detects. Okay, this is how it computed with just one frontal face, and this is the output on my own face. Let's check it for another image. And as you can see, with definitive accuracy, it is detecting on single frontal faces. Thank you.